So with bonding, we've already talked about the octet rule, but just to remind you, there we go. Atoms are going to, or elements are going to try to gain sometimes electrons, so sometimes lose electrons, and sometimes they'll share electrons so that they get a full octet. Now, if I'm talking about the first energy level, which is N equals 1, this is that first, period in the periodic table. So that's full shell is 2 electrons, because helium has 2 electrons. And then all the other energy levels, this is the second period in the periodic table to the 7th period in the periodic table. They all need 8 electrons to have a full octet. Now, that means that I want to have a full s orbital, and I want to have a full p orbital, full p subshell. Excuse me. So if I walk over to the periodic table, what that looks like is, I need to have the periodic table in front of the line. If we're thinking about, krypton, right? Krypton has its 4s subshell full, 4s2, right? That's full, and then 4p6 is full. And so 1, 2 plus 6 is 8. These are, if you think about it, those will never be valence electrons. The d orbital electrons will never be valence electrons, because this is 4s2, this is 3d10. So it's only the outermost energy level that is a valence electron. And so you'll never have like 18 valence electrons. Only 8 is the maximum number. All right. So we were looking at this in the wrestling room, and metals are going to become positively charged. So what that is, if they're playing tug of war, right, they can't pull very hard, and so they're going to lose the rope, which is the electrons, to the nonmetals. The nonmetals have a higher electronegativity value. So I want you to take your periodic table, and I want you to take page 265? Page 265, and I want you to look at the data on the periodic table, and I want you to fill in the trend one more time for electronegativity. So increasing which way, decreasing which way on your periodic table, side of your dry erase board. Yeah, just arrows, and then label the arrows with increasing, decreasing, whatever. Well, look at the numbers. What happens? There's nothing like a brand new dry erase marker. So, well, at least in the and you don't even really need this chart data. You can remember it's opposite from atomic radii, whatever you like. But this is what to do. I did go back and fix y'all's test and give y'all 3 extra points. Yay. This reminded me of that question. All right, couple people still working. Finish up. All right. Good. Good. Okay. And looking at electricity. Yeah, that's fine. Good, thanks. And so electronegativity actually increases here because you're adding more protons and protons are what's pulling the electrons, that positive pull. Okay. Hello. So if we think about the tug of war game, and we're playing tug of war, as we go across the periodic table to the nonmetals, the electronegativity increases, and so those nonmetals can pull in electrons harder. As atoms get bigger, those that bonding atom is farther away from the nucleus, and so it decreases this way. We all had that by the time I got around to everybody. So it increases as we go across the group and decreases as we go down. Like the most depressing thing I've ever seen in my life was the fact that, you know, your slope for this test is just like, what's the trend for electronegativity? It doesn't go into like anything other than these arrows. But, you know, at the end of the day, you'll know so much more than that, which is, I think, a good thing. Anyway, so if we look at electron configurations, for sodium, for example, it's 1s2, 2s2, 2p6, and this is your 3s1. That's that one valence electron. And so when sodium loses this electron right here to become like neon, you can see that it does get much smaller. So cations are smaller because now we lose a whole energy level. And so it has a full octet now, but it is missing that third energy level. And that's kind of a review from last unit. That should feel very comfortable and like you already have that in your brain. With chlorine, chlorine is going to gain that electron probably from something like sodium. And so chlorine is the guys, chlorine pulls on the electrons very hard, and it's going to steal the electron, which is the rope, away from the sodium, and then it's going to have a full octet. And if you notice, they did a good job in this diagram making the chlorine, or excuse me, chloride ion larger. So, and you see here that the s orbital and the p orbitals are full, 3s2 and then 3p6. You already should know this. If you don't know this, I don't know how you've been surviving. But group 1 is 1+, this is 2+. We'll tell you that, you know, some of these, like on group 15, that's the group with like nitrogen and phosphorus. It's 3- as far as we're concerned. It can be crazy stuff. Don't worry about it. And then remember, and this is something that I'm expecting you to know now. Like if it's on a quiz, like this is on you. And, you know, this was actually on your quiz yesterday, but tin and lead can be 4+ or 2+. So I'd already told you, but I'm telling you again, that you need to kind of see what they're bonded to tell the oxidation number. Excuse me, the charge, same thing as oxidation number. And so you have to give me the Roman numerals on tin and lead. Roman numerals. Okay? So then group 16, which is 6A. 2-, this is oxygen and sulfur, for example. And then group 17, chlorine, bromine, iodine, they're 1-. So that should be, you know, okay, I got it. The D block. Oh, the D block. I do want to talk about this because y'all always ask me about it. Talk to your neighbor and tell me, after you talk to your neighbor, what's the maximum number of valence electrons an element? I'll pick one for you. How about nickel? Or something maybe like rhodium. Think about nickel and rhodium. So that's, you know, Ni and RH. What's the maximum number of valence electrons that they or any other element in the D block would have? Talk to your little group. Think about their electron configuration.
Yeah, well, everybody has on the outside, but it won't be from one part or
Think about what valence electrons are anyway.
She said that it just takes a little like 4s and then yeah, 3 like 3D thin going to be 1 less than the 4. So those will still be in there. Oh, that's what she said earlier.
No, she said that like because of that reason they wouldn't have
How can you? There's no way to have no valence electrons. So you're always gonna have electrons on the outside unless you have no electrons in your proton. Unless you're a hydrogen ion.
Yeah, that's it. I got the answer. This is something, I mean, I'm just telling you this because y'all always ask me, why is it a lot special? Because I'm telling you right now why. Because stop asking me. Okay, judgment free zone on this question. This is kind of like a freebie since y'all always ask me crazy questions. Lucy H, what did you guys guess?
We were talking about are the valence electrons the numbers in the formula? That has to be.
So how many valence electrons are you thinking that nickel might have? 10. So you're thinking that you have. Okay. So let's write the electron configuration, and I don't expect you to know this, and that's why I'm asking you, because I want you to go in your head. I don't know. Oh, avert your eyes, right, Chelsea? Is Chelsea in here? Yeah, that was bad. So if I write the electron configuration for nickel, I'm going to do the abbreviated version. So I'm looking at argon, the noble gas one. Argon, and then 4s2, and then 3d, I don't know, 8. So here's the definition of valence electron. The electron's in the outermost energy level. So if I write it like that, think about it.
Then it has 2.
How many valence electrons does it have? In the outermost energy level, the highest energy level. Just 2. And so when we're looking at those transition metals, most of the time, you know, they can have several different charges, but most of the time, one of those 2 charges is 2+. Like copper 1 and copper 2. You got iron 2 and iron 3. And then like zinc is always 2+. You know, cadmium is always 2+. You have some that are 1+, but the reason most of them have at least a charge that's 2+ is because if you're removing electrons, like those are gone, right? And so that's your 2+. And so like iron that can be 3+, if one of those D electrons will get gone. And the D orbitals look like crazy sideways donuts that are, I can't even tell you what they look like. They're like unspeakable. But they're really close in energy to those 4s electrons. These are really close. So if you take these, if they're removed, it's not too hard to get one of these. I mean, but if you were ever curious, that's the deal. Like that's why they can have multiple charges. Because they'll lose these 2 valence electrons. But then these aren't that much different in energy. So some of those can get plucked away as well. So, fun times. Does anybody feel okay? I kind of understand all that now. Okay, I know that's y'all been asking me. So there. So if we look at iron right here, there's iron 2, and you can see it loses those 4s electrons, and then iron 3+ will lose one of the d electrons. So that's the issue. There you go. Ionic compounds are when one of the teams like completely hexaroten. So that's going to be the nonmetal. And so you're going to actually form a cation and an anion. A positive electron, a positive ion, and a negative ion. And I think that, now, this is just fun facts. Do you care? I'm going to tell you something interesting. I don't think other countries call negative ions anions because I've had one guy in Australia and one guy in Canada. And I don't know if they keep saying that I'm using this has happened twice, that I'm using a clever pun when I say anion. Because they're like, oh, I get it, a negative ion. And I'm like, no, dude, that's in my book. But I don't know what to say. I'm like, am I being weird? But an anion is totally a thing. But I don't know if, like, every country calls it that.
What do they call it?
I don't know.
Ask them. Like, next time, be like, what are you talking about?
I don't know. I might send somebody, like, I might message them so I don't sound like an idiot. I'll let you know. I'll let you know. But no, I've had 2 people like, oh, I get what you're doing. I'll remember who sent me that tweet. I'll pull it up. I'll prove it to you in a minute, if you care. Maybe you don't care, but I thought it was interesting. Ionic bonding is where, I might want to highlight this. It's where metals are going to transfer electrons to nonmetals. I just talked about that. Or sometimes you might have your polyatomic ions. They do the same thing. But the issue is they're held together by electrostatic attractions. That just means opposites attract, so they stick together. One's going to be positive, one's going to be negative. It's not like that's not rocket science. They just make it sound like this. And remember, this can include polyatomic ions. So something like carbonate, you know, which is 2-, it's going to pull on electrons in your metals, and well, it's going to. That's where it gets the 2- from. So ionic bonding, if you want to see what that looks like, here's sodium with 1 valence electron. That valence electron is transferred to chlorine. And so now I have sodium 1+, and chlorine has an extra electron. When we draw these Lewis structures, have you ever done that, like written the element symbol and then put dots around it? Is that like ringing a bell? Alright, so if we were doing something like carbon, you ask yourself, well, how many valence electrons does carbon have? And so if it's 4, which it is, it's real hard. Nitrogen has 5, right? So You just put one at a time, and then they groundbreaking stuff. It gets a lot worse than this. But this is this is where we'll start on Monday. And so that'll help us as we understand the bonding. I really like drawing the Lewis structures and the 3D stuff. I don't know how much of that we'll do, but I put it all in your little packet. So I'm hoping we'll get, at least with some of y'all. This lattice energy stuff, because I had several people not do super good on the quiz, I'm not going to talk about this a lot, but maybe on Monday, as people are studying naming the people that get it really well, I might pull y'all aside and talk about this. So for right now, maybe just, I'm not going to have this on a quiz or anything, maybe just X through this in the corner, and not to study it for a quiz. I don't want you to the night before quiz to be studying and freaking out, right? So just put a little X on this and this. Hey, there's Coulomb's law. Do you remember him? Opposites attract, that guy? Yeah. Okay. There's his formula. Good times. Oops. So you don't need to worry about this. Okay, so covalent bonds. Covalent bonds are like when we were playing tug of war and nobody really was winning. The electrons of the rope in that case was being shared. So one atom shares electrons with another atom, so they both acquire full octets. And so this is going to happen between two nonmetals. And so the reason that that happens between two nonmetals is because if you have a metal involved, the metal will give its electrons away. So, and this is kind of where we're going to start using that chart in your book. So, anyway, here is the definition of bonds. And so, when we've been talking about bonds, and we said, oh, this is ionic and covalent, like that's the 8th grade definition, but you're not in 8th grade. So let's just take it a little bit further. You ready? So if I look on my little chart here, you have electronegativity values in your textbook on page 265. And so if I take those, and let's say that I have a bond between something like bromine and chlorine, right? Let's just say that I have something like this. If you take the electronegativity value of chlorine and subtract the electronegativity value of chlorine, bromine and chlorine, I said it twice, whatever. So if you take that and you subtract it, you get 3.16, and this is just in the chart for electronegativity values, minus 2.96, and you get a difference of 0.20, I think, whatever. So, is that what the book has? Yeah, okay, cool. And so that means that if I think, okay, which side is going to be pulling on the electrons more, they're both about the same strength, and they're both pretty strong. And so when I subtract, if that difference is less than 0.5, then it's a covalent bond, okay? And it's called a pure covalent bond, where it's really, the stuff's right in the middle. Now, sometimes, fluorine, for example, let me erase that, or oxygen, y'all breathe oxygen, right? And it's not like O. Did you know the oxygen in the air is O2? Did you know that? Well, that, I don't know what you know, but I'm going to teach you that. So, oxygen, this is an oxygen bonded to another oxygen. And so, if I take the electronegativity value of oxygen, which is 3.something, 3.44, and I subtract 3.44, what do you get? 0. So that is a true, nice, pure covalent bond. So, if I have two oxygens, you can think, okay, well, one's not going to pull harder than the other, the same element. So moving on down to the road a little bit, sometimes, like in our warm-up, sulfur and fluorine, for example, sulfur is not as electronegative as fluorine. Fluorine is the most electronegative element. So what I want you to do on your little chart here, your periodic table, I want you to find sulfur and fluorine, write the electronegativity values in your periodic table, and I want you to find the difference and tell me if it's a polar covalent bond or just more of a pure covalent bond where they're equal. So you're using the chart of electronegativities in your book, and you're finding this. Let me do. for the people at home. Oh, it's not going to work. Okay, let me get my internet. Yeah, so sulfur and fluorine with the F. Thanks. Here we go. This one's in color. Ooh. So sulfur on this one is 2.58 and fluorine is 3.98. And so that's a difference of 1.4, right? So, I guess. Sometimes, I don't know, if you're good at mental math and you just do stuff, do you ever like guess if you kind of second guess yourself? Does anybody have that problem? Good. That makes me feel better because some people are like, I don't know how to add. And that's totally fine. Everybody's special and wonderful. I lost my PowerPoint. It's probably up underneath here. There it is. Alright, so I just said the difference was 1.4, so that's polar. That means that the electrons are spending more time near the near the fluorine. And I know they're spending more time near the fluorine because the fluorine can pull harder, has a higher electronegativity. The definition of electronegativity is how hard the electrons are being pulled on in a bond by that atom. So, anyway, y'all know the definition of an ionic bond, don't you? Do you know the definition of an ionic bond? Well, prove it to me numerically. Can y'all think, what's a good, like sodium chloride, right? Let's do that. Find sodium on your periodic table and fluorine on your periodic table. Write the electronegativity values and subtract them and see if it actually is electronegative. Or, excuse me, ionic. Oops. So sodium is on mine 0.93 and chlorine is 3.16. Which one?
I feel like I'm just not saying.
You can make you can make stuff with that. So yeah, 0.93 and then 3.16.
So is that like because like have like d electrons?
The reason for this, yeah, once you right, and then if we look at radon, that distance is too far because the energy level. So if we look at xenon is smaller, but yeah, that's definitely has something to do with it, and that's the reason that you can like forcibly make like xenon, like I think it is right. And I know the shape of it, and we'll do that next year. But that's why you can do it, but you can't do that with like neon because it doesn't have the d orbitals. All right, so when you subtract, you should have got like 0.19, I think. The electronegativity value of sodium is 0.93, and the one for chlorine was 3. And so you should have gotten oh, Lord help. I was just looking at it, and all right, tell me the electronegativity value of chlorine. And then the one for sodium is? 0.93. Okay. And so you get, what?
6 minus 3. I'm just saying. What?
No, you get.
Now you borrow from the 3.
Yeah. And then I did that.
And then decimal.
The reason this is funny is because in AP Environmental Science, I spend a few days teaching people how to subtract, add, divide, and multiply. That's funny. Like, I can basic math anybody, like, under the table. But I don't know what I think when I was looking at it, I was having a conversation about crazy stuff. But anyway, the difference is definitely greater than 1.9, so it is ionic. So metals and nonmetals. The reason that ionic bonds have to be metals and nonmetals is because when you subtract them, you need this difference. And so chemists don't go, oh, it's a metal and nonmetal. So there's this gray area where things are kind of borderline. So, moving on, let's go ahead and do a little bit more with this. So a pure covalent bond is anything with 0.5 or less. And so, really, like, technically, that 0 where you have two of the same, because fluorine minus fluorine is going to be 0. That's a covalent bond. This is hydrofluoric acid, but it's also a gas. I don't want to talk about that because it's going to confuse you. Hydrogen is less electronegative than fluorine. So what I want you guys to do is I want y'all to take your periodic tables in your book. You don't have to necessarily fill in your personal one, but you can if you want. But I want you to do the electronegativity difference for F2, and then HF, and then sodium fluoride. So do the math and prove it to me that these are pure covalent, polar covalent, and ionic. You should have this 2 decimal places. We're done. I was just asking about sig figs. Remember the rule of sig figs is it's the decimal place that you're limited by, so your answer should have 2 decimal places. And it could have a number in front or it could not. And I guess if your answer is 0, then it's 0. I don't think I drank my coffee this afternoon. Nope, it's completely full. I can always tell because I do dumb stuff. Yeah, what? Yeah, I make it at lunch and then sometimes I forget to drink it. So that cup is really good. It'll keep hot for a long time. But I was putting your grades in the computer, so y'all have your subtraction done? Good times. Yay. No. Yes. Alright, so let's pick some victims. Students. I'll do the first one. 0. Allie, what'd you get for the second one when you subtracted?
1.7.
Okay, 1.78. And notice how close this is to being that 1.9. So this is like that borderline. And when you make, this can be a gas or an acid if you put it in water. But you still need to, when I'm showing you some stuff that has hydrogen and F, like still think about this as hydrofluoric acid and how this has to be 1 plus and 1 minus. Like, it's not worth delving into that too much. But it's very close to that 1.9. But it is polar. And then Thomas, what'd you get for this ionic sodium fluoride here?
3.05.
Sure. And so that's definitely over that 1.9. So we're totally ionic. The fluorine has stolen the electrons from the sodium. So good. Yay, we're doing the things. Moving on. Whoops. And so here's some more examples. Hydrogen gives you a 0. So polar covalent, and this is carbon dioxide. Notice the difference there is 1. This lithium fluoride, you would expect that to be ionic, and it is. You have electronegativity difference of 3. Do you have a question?
Yeah.
Sure.
Are there any elements that you can put together to where the electronegativity will be 3.5? Or yeah.
So when you do the difference, the least electronegative stuff would be, metals all the way. Well, look at your textbook, all right? And so let's look at the chart. I have a chart up here. So
like I was thinking, francium with like fluoride, that come close, but it doesn't.
well, if fluorine is definitely the most electronegative, and looking here, I think that one is the least. So I guess not. But that's a good question. And that was easy, since we knew our trends, it was an easy question to answer because I knew it was going to get less as I went down and get more as I went across. So, so there's that. And then I would expect that to be ionic, and it is. Please, for the love of all things holy, you can call a covalent two non-metals. You can call that a molecule all day long, and that is fine and that is correct. You cannot call something with electronegativity difference of over 1.9 a molecule. You can't. It's called the formula unit. So ionic compounds, they are called formula units. And so if I'm looking at NaCl or any other ionic compound, then it's going to be called a formula. That is a formula unit of salt, not a molecule of salt. You can't say that. You can actually, if you wanted to know, you can call an acid a molecule because it's all non-metal. So you can say a hydrochloric acid molecule. But yeah, yes, sir.
So are all ionic compounds like, are they all salts?
Yes, they're all solid, nice, crunchy. They're not all white, but yeah. If I take you to the stock room and there's a whole cabinet full, you guys that are AP chemistry, you'll get to know it really well. And they're all in bottles, and they're like little grains of stuff. All of these things but are ionic. Yeah. So there's no liquids or anything. There's reasons for that, and my face hurts thinking about it. I'll get to it next year. Yay! All right, so there's that. What I want us to do, if you look at your homework, I'll leave this on for the people at home. What we're going to do today is you have a practice sheet that's connected to the back of this. You are going to skip. You are going to skip numbers. You're skipping 6 and 7. And I'm going to put the answer key up. The answer key was, you remember that one time we did these and it was like giant paragraphs of ridiculousness? That's what the answer key was looking like. So I was like, nope. So I'll put up some answers to this. And so I want you to work on this and check your answers as we go. If you don't finish this in class, it's not homework because you don't have the answers to check. And the last couple are tricky. What is homework and what you have to do before Monday, this is what I'm checking on Monday. This we'll work on in class some more. But I want you to do this first. I want you to do this covalent, or excuse me, chemical bonding. I want you to do this first. If you should happen to get done, what is homework for Monday is the first page of this. It says the two papers that are stapled together that are real small font. It says ionic bonding practice and advanced ionic bonding practice. So just that front side. The back side probably be homework on Monday. So if you just feel real industrious, knock it out. But do yourself a favor, do the work, and then check it with the answer key. Mercedes has been doing an awesome job with that. Like, I can tell she does it and then gets a red pen and checks it. At least check your work. I can't do anything for you if you won't check your work with the answer key I give you. I can't do anything with that. Alright, so I think y'all learned y'all's lesson yesterday, but in case you didn't, there. So that's what you're doing for me. You're going to finish up this. I'll put the answer key up here in a minute and do that first.